This is the fourth video over Chapter 4, Newton's Laws, and it's on Newton's third law. This is Section 3 in your textbook. So we talked about forces in the very first video. A force is any push or pull, right? Any push or a pull. I bet you can already state Newton's third law. For every action there is, right, an equal and opposite reaction. But what does that mean? For every action, there's an equal and opposite reaction. What that means is that every force is actually an interaction between two objects. A single object can't act on a second without that second object acting back on the first. And the force that the second object acts back with is an equivalent force. So right now you're probably sitting in a chair. I'm sitting on my bed. So right now, the bed is pushing up on my backside, just like the chair is pushing up on your backside. Well, you are pushing down on the chair, and those two forces are equal and they're opposite, and they are called a reaction pair. We'll talk about reaction pairs a little bit more in just a minute. Contact forces and field forces are both subject to Newton's third law. Every force, regardless of the type, is an interaction between two objects. If you hit something with your hand, you can't hit it without it hitting you back. There is an interaction when the two things are in contact with each other. Forces happen in pairs. It's an interaction. How do birds fly? Well, you know that birds, when they flap their wings, and so as they flap their wings are pushing down on the air, and the reaction force would be the air pushing back up on the bird's wing, and this is what gives the bird lift. How do fish swim? Well, the same way you do. When you swim, if you're underwater, think you push your hands back through the water, and the water pushes you forward, propelling you forward. So you push the water back, and the water pushes you forward. Well, how do you walk? Well, think about how your foot comes in contact with the ground. And as you put your foot down and you shift your weight forward and you push off with your foot. And so your foot pushes against the ground and the ground pushes back. There's a frictional force there. And so that friction between you and the floor, you push back on the floor and the floor pushes you forward. Well, you're the thing that moves forward because the floor is not movable. Have you ever seen like lumberjacks running on logs that are in the water? Well, they run, but the log just goes around and around, and they run and they run and they run because the log can move. If the lumberjack were standing on the floor and needed that, he would move forward because the floor is not movable. In your case, if you're walking, you get propelled forward, and the floor don't get pushed back. You're the lighter thing, you're the movable thing. How do helicopters fly? Well, those rotors on top of helicopters. Ooh, I don't draw a very good helicopter. The rotor on top of the helicopter, I missed, didn't I? Pretend that's a little bitty axle. These things go around, and they're shaped like a fan blade, and they push the air down, and the air pushes them back up, and they get lift that way. How do cars move? Well, the same way you walk. The wheel pushes back on the road, and the road pushes the wheel forward. How do boats move? Motors and paddles. Well, have you ever paddled a boat? You stick the paddle in the water, and you make sure that its broad side is moving through the water, that it's not slipping through on its narrow side, and you push the water backward, and the water propels your boat forward. So each of these is an example of an action-reaction pair. Forces happen in pairs. One thing can't act on another without the other thing acting back with the same amount of force. It's sometimes useful to identify these pairs. They're called interaction. They're also called action-reaction pairs. I've tried to be consistent throughout all of the worksheets and stuff that you'll be looking at, but if I haven't been, action-reaction pairs and interaction pairs are the same thing. So how can you tell if it's an action-reaction pair? Well, it's easy. It's a pair. There are only two objects mentioned, and they switch places in the statement. Object A acts on object B, Object B acts on object A. The bird's wings push down on the air pushes up on the bird. When you're walking, your shoe pushes back on the floor pushes you forward. So two objects, and they switch places, one being the actor and the other being the recipient of the force. If we look at the examples on the last slide, we can identify the reaction pairs. We kind of did as we went through. The bird pushes down in the air pushes up on the bird. The fish or you push back on the water pushes you or the fish forward. You push back on the floor pushes you forward. The helicopter rotors push down on the air pushes the rotors and then the helicopter up. The tires push back on the road pushes the tire forward, and the same thing with motors and paddles. So let's look at this picture and see if we can pick out some action-reaction pairs. What do you see? Well, let's start with this guy. He's pushing back on the road, and the road's pushing him forward. That's an action-reaction pair. Well, there's some tension here. This strap that he's hooked to the truck with, it's pulling him back, and he's pulling it forward. Well, and here, it's pulling the truck forward, and the truck's pulling back on it. Look at this guy. He's pushing down on the bench, and the bench is pushing back up on him. Can you see anything else? I didn't mean to write that last thing. The car's tires, they're pushing back on the road, and the road's pushing forward on them. So do you see how it works? Okay. Same force, different mass, means different acceleration. A bug and the windshield of a bus collide. Upon which is the force greater? Newton's third law says every force is an interaction, and the force that object A exerts on object B is the same as object B exerts on object A. So while the bus might be really, really big, and the bug might be really small, when the bug collides with the windshield of the bus, the forces that they exert on each other are equal. Now, that's not to say that they're impacted the same. It's not to say that the effect of that force is the same. Of course, the bug has the much greater life-changing effect of the impact there. And it is the acceleration of the bug that is different than the acceleration of the bus. You jump up, you fall down. If you're pulling up on the earth with the same force with which the earth is pulling down on you, why doesn't it rise to meet you? Well, the earth's really, really big, and you're really, really small. So you jump up, you jump down. The earth is so massive that that force doesn't cause much of an acceleration. Now, it's hard to talk about this without ever having talked about Newton's second law, so I'm going to sneak that in. Newton's second law, as you'll learn probably in the next video, is F equals ma. A force exerted on a mass results in a certain acceleration, a, or a equals F over m. I've just done a little algebra rearranged. So that force on a really, really massive thing, see m's in the bottom, if the mass is really big, there's a small acceleration with the exact same force. So the Earth's mass is really large. There's almost no acceleration. Your mass is not so large, it's a much larger acceleration. And the same thing with the bug and the bus. And the bus's mass relative to the bug is very, very large, and so the bus's acceleration is pretty much nothing. The bug's mass is really small, and so that force is enough to really accelerate the bug. And the bug's exoskeleton is probably not strong enough to withstand that kind of an acceleration, and so it loses structural integrity. So you have a gun. I'm not good at drawing guns either, but so here's a gun, and there's a bullet sitting inside this gun. When you pull the trigger, there's an explosion in here. Hot gases expand and send the bullet this way, and the bullet leaves the gun, moving with some high velocity. If you've ever shot a gun or watched much TV, you know that guns recoil. If the bullet is sent in one direction, the gun exerting a force on the bullet, there will be a force on the gun it's the same force in the other direction. So guns kick back, and it's a Newton's law thing. The gun pushes the bullet forward, and the bullet pushes the gun backwards. The bullet has a much smaller mass, so it has a much higher velocity. Suppose you were trying to outfit a spy with a gun that would not be detected by metal detectors. Also suppose that there's this new plastic that could withstand the heat of firing a bullet. Why might using this material be a bad idea? Well, remember, the acceleration is inversely proportional to mass. And so the bigger the mass of the gun, the less velocity it's going to move back with. So if you've got this lightweight plastic gun with a very small mass, then its acceleration backwards is going to approach the acceleration of the bullet forward. It's not really a good idea to have a gun moving backwards with the same speed that the bullet's moving forward. You end up hurting yourself as bad as you would be hurting someone that got hit by the bullet. So bad idea, because the mass of the gun would be so small. Action, reaction versus equilibrium. You're pushing down on the seat of your desk. The desk is pushing back on you. Is this an action-reaction pair? Let's see. You are pushing down on the seat, and the desk seat is pushing back on you. Yeah. So two objects, just their roles are reversed. Yes, it is an action-reaction pair. So these forces cancel to make equilibrium. Well, no. In order for forces to cancel, the net force to be zero to make equilibrium, all of the forces have to be on a single object. So here's you. Let's look at the forces on you. Gravitational force is acting on you, and the normal force, the support force, is acting on you. Those two forces can act to give equilibrium, but those two forces are not an action-reaction pair. The seat on you, the earth, that's the gravitational force, on you. That's not an action-reaction pair. Look, there are three things: the seat, you, the earth, and well, there's you again. That's three things, not a pair. And all of these forces are on you. In order to be an action-reaction pair, the thing acting and the thing receiving the action have to switch places. You on the seat on you. That's an action-reaction pair. So action-reaction pairs do not add up to be equilibrium because they're not acting on the same object. It's the same force, each object acting on the other. Tension and normal force are both reaction forces. Tension is a force in a string or a cord. If you have a box that's tied to a string, until you start pulling on this end, there's no tension. But as soon as you start pulling on that end, so erase the droopy string and make a tight string, when you start pulling on it, there is now tension in that string. You are pulling on the string, and the string is pulling back on you with a tension force. The box is pulling back on the string. Its inertia is holding it in place. Its mass, its weight are keeping it from moving, and the tension is pulling back on the string. So tension is a reaction force. The normal force is also a reaction force, and when you talk about it, so you're going to have to calculate normal force. You are sitting in your seat. The earth is pulling down on you. Your seat is pushing up on you, and you're not accelerating. So that means that the normal force minus your weight, and I say minus because your weight is down, and the normal force is up, and up is positive and down is negative, equals 0. And so that tells me that the normal force must be equal to your weight. Now we talk about how to calculate weight. We talk about Newton's laws, but we'll go ahead and say mg is weight. It's the gravitational force acting. Mass times gravitational acceleration. So the normal force of an object that's just sitting is equal to its weight. Now the normal force can change. If you have a box and you, oops, I drew the hands wrong. Don't you love my artistic capabilities? You push down on the box. Then you're going to increase the normal force. Now if we look at the forces acting on this, we have weight we've got the normal force, and we have that downward applied force there. So we have another force acting down. Let's say FD for down. So if we add all the forces together, the normal force minus mg, because it's down, minus that downward force equals 0. There's still no acceleration. So in this case, the normal force equals mg plus that applied downward force. So the normal force is bigger. Well, there's more force pushing down, so the floor that's supporting it has to push back with a greater force. If, on the other hand, you had a string tied to this, give you a head, had a string tied to this box and you were pulling up on the string, now if I look at the forces, I've got the normal force, I've got weight, I've got the normal force acting up, and I've got this upward force, F up. So if I do an equation, I'm adding all my forces together, the normal force plus that upward force minus mg equals 0. It's not accelerating. The net force is 0. It's not accelerating. Let me get back to what I was doing. So the normal force now is equal to mg minus that upward force. So it's lessened. If you lift up on the box, the floor doesn't have to push as hard to support it. Okay? So the normal force can equal weight. It can be bigger than the weight if there's an additional downward force, and it can be less than the weight if there's an upward force. The normal force is not always straight up. If I have an object on an incline, the weight is still acting straight down, but remember normal means perpendicular. Perpendicular to the surface, the normal force would be at an angle. In this case, the normal force would also not equal the weight. It's got a trig function in it. We'll worry about it in the next chapter. But you need to know that the normal force can equal weight, but doesn't always equal weight. It can be greater if there's an additional downward force. It can be less if there's an added upward force. And it can be off at a different direction if your object's on an incline. And that is the end of our Newton's third law lecture. Thank you.